Hello, so this is a revision video for AP Chemistry 7.3, Reaction Quotient and Equilibrium Constant. The reaction quotient Q is a snapshot of a reaction's progress. It is calculated by using concentration values of everything in a reaction mixture at a specific point in time. For the general reaction A plus B going to form C plus D, the expression for Q, the reaction quotient, would be concentration of C raised to its molar ratio in the equation, times by the concentration of D raised to its molar ratio, divided by the concentration of A raised to its molar ratio times the concentration of B raised to its molar ratio. So it's basically a way of expressing the ratio of products in the mixture compared to the concentration of reactants in the mixture. Note in these expressions, the square brackets mean concentration in moles per litre or molarity, M. The equilibrium constant K uses the same expression as Q, but only applies for a system when it is at equilibrium. Now, K is only valid for a given temperature and does not change unless the temperature changes. This sounds confusing, but what it really tells us is that when a system is at equilibrium at a specific temperature, the ratio of concentration of products to reactants in the mixture will always equal the value K. When writing expressions for Q and K, we only include gases and aqueous species. We don't include solids and pure liquids, because their concentrations can be considered constant, or more technically, their activities. The value of K tells us the position of equilibrium for a given system. So, for example, if K equals 1, the system is balanced. Neither the forward nor reverse reaction is favoured, so the concentrations of reactants and products are comparable. In other words, the position of equilibrium lies in the middle. If K is greater than 1, that means there must be a greater proportion of products in the mixture compared to reactants. In other words, the top of the fraction in the expression is bigger than the bottom of the fraction. This tells us that the equilibrium mixture contains a higher proportion of products than reactants, so we say the equilibrium favours products and the forward reaction is favoured. Equally, if the value of K is smaller than 1, this tells us the bottom of the fraction or expression is bigger than the top, so there is a greater proportion of reactants than products in the equilibrium mixture. We say the equilibrium favours the reactants, the reverse reaction is favoured. In simple terms then, the magnitude of K gives us an insight into which side of the reaction is dominant at equilibrium. The bigger the value of K over 1, the more the equilibrium favours the forward direction and the products. The smaller value of K under 1, the more the reverse reaction is favoured and the equilibrium favours the reactants. In the AP Chemistry course, you encounter two main types of equilibrium constant: Kc, which is based on concentrations, hence the C, and Kp, which is based on partial pressures, hence the P. Partial pressures only apply for gases, so Kp can only be used for gas-based systems. Kp works in exactly the same way as the equilibrium constant for Kc. The total pressure of a gaseous system at equilibrium is directly related to the number of moles of each gas in the mixture. How much pressure one type of gas contributes to the total pressure of a gaseous system is called its partial pressure. All partial pressures of gases in a system add up to give the total pressure of the system. Partial pressures can be calculated using the mole fraction of a gas times the total pressure of the system. The mole fraction of the gas being the moles of that gas in the mixture compared to all moles of gas. So it's calculated by taking the moles of that particular gas and dividing it by the total moles of all gases in the system. We can compare the reaction quotient Q for a system to an equilibrium constant K to predict the direction in which a reversible reaction will proceed. This may sound complicated, but it really isn't that bad. If the value of Q equals K, then the system is at equilibrium. Because, remember, the value of K is the proportion of product to reactant concentrations at equilibrium, whereas Q is the proportion of product to reactant concentrations at any given moment in time. Well, if at any given moment in time the proportion of product to reactant concentrations gives the same value as K, then the system must be at equilibrium. However, if the value of Q for a system isn't the same as its equilibrium constant K, the system can't be at equilibrium. But the reaction will proceed in the direction that moves the value of Q towards K. So if Q is less than K, the reaction will shift in the forward direction, towards the product. Over time, this means the value of Q will get bigger until eventually it equals K and the system is at equilibrium. If the value of Q is greater than K, then the reaction is going to proceed in the reverse direction, towards the reactants. Over time, this will mean the value of Q gets smaller until eventually it equals Q, and then the system is at equilibrium. Exam tip here. It's really important to compare like with like when using Q and K. For example, if your equilibrium constant is a Kc value, then you must use concentrations for your Q expression, Qc. Equally, if your equilibrium constant is Kp, then you must use Qp values based on partial pressures. You can't mix Qc, for example, with Kp.